But it's really, we need this, okay? You know, so it's really important to stay awake anyway, because, you know, when we get to like thinking about how to regulate the grid with a lot of renewables, we have to understand grid dynamics. And, you know, so far, you know, I hate to put this down again, but I'll just try to recall this big bunch of spaghetti, you know. So we had a control loop. Okay, so the balancing authority sends this load set point, and U is, what the notation I've been using is rho sub V for the valve position. And in the book it's called P sub valve. And you can see why I didn't like that notation. I called it rho sub V. So I decided not to change my notation. So if you look at the lecture notes from last lecture online, I'm still see it using rho sub V. But I do say it's the valve position, okay? So all we're doing is we're adjusting the valve position in all of this. And I'm making a slight change in notation here, but not for long. The only reason for introducing this artificial notation temporarily is for those of you who have taken a control course. And, you know, basically, normally you take an error signal, which is E is defined as what you want minus what you've got. So in control, that's the typical notation, is what you want minus what you've got. But the definition of delta omega is the opposite. So that's why that's why the control loops look really funky in the book, if you're a control person. All right, and so this is what we get for the transfer function from a error signal to the input, which is again this valve angle. And their dynamics then. There's dynamics in this physical system from valve position to power, and that by normalization and approximation is modeled as a first order linear system. So there's one thing that has to do with physics, and this is something about design. So this whole thing, this would be called G sub C in a control course. And that's the main thing that makes control a difficult subject, is you often can't tell what is physics and what is in a computer. So this is on a computer, you know. This is something, you know, you're making decisions. Based on error signal, you're making a decision on the valve angle. And this is a crude approximation of the physics of valve position to power. You know. And it's natural to be a low-pass filter because when you suddenly change the valve angle, you don't instantly change the power. There's some ramp-up time for it to change. And we can go and play with these things. So last time, I only looked at the DC case. You know, I looked at, last time we looked at the static, sort of the steady state response to a increase in load. And more generally, we're really looking at a steady state disturbance response. So a generator shuts down, unexpectedly, and you don't do anything at all. You just keep this control loop in place, but don't bring any other resources involved. What is the new steady state frequency? What's the new steady state power? And so forth. And we worked out a cute formula for it. It's, all right, what the hell? Isn't that right? Well, hold on. I think that's right. Tell me if I'm wrong. Wasn't that what it was? Yeah. Inverse. Yeah. Right. So if all these Ri's were the same, say, and n was very, very large, then the frequency wouldn't change very much. So the steady state behavior depends on how many guys are involved and what these droop characteristics are. That's a droop. One of R is a droop gain. All right, so the thing is that that's just a steady state. So we want to talk about control for lots of reasons. Because, again, we have a disturbance rejection problem. We've got disturbances from nature because of volatile renewable energy, which is in a massive scale, nothing like seen before. And in order to think about control, you first have to have a model of the system to be controlled. And we have all these distributed inputs here. Basically we've got these little microcontrol loops making decisions. But later on we're going to have a lot of fun with this. That this God, the balancing authority, off there somewhere, like in PJM, this massive, 1/3 of the US, there's a little control center near Albany, New York, and they send the signal to all of the generators under them to manipulate them and make them do what they want. And now today that's done by generators. I hope that in 10 years it's done by other resources as well, and probably much more cheaply. And that balancing authority is going to still play a role, and we want to understand how in the next weeks. So this is all very dear to my heart now. This is getting close. I broadcast an email message this morning explaining how this is getting closer to my own research. Okay, so how do we tear this apart? So first of all, we have to go beyond steady state. And so we got to take Laplace transforms. I made a joke that that's not a Lagrangian, it's a Laplace transform, but let's do it again. So we've got minus delta omega coming in. And I'm going to drop this load set point. So you all know that if you have a system with two inputs, you can look at them individually. You can first pretend that's 0 and look at the response from this, and pretend that's 0 and look at the response from that. The principle of superposition should have been taught to you in signals and systems. And so I'll take that for granted. So let's forget about that. And let's bring this around. And then we can go and play, and we can unravel this. And what do we get? So by definition, this means U of S is equal to this transfer function times minus delta omega, that was time domain and that was frequency domain, but I'm using the same symbol. Sorry. And then minus R times U of S. And we can then unravel this. It's easiest to multiply through by S. You know, if I multiply both sides of this equation by S, I'll get an S times U of S, and I can cancel. Okay. And what will I get? Well, we can do this all in our heads, right? We're going to get a kg times R with a minus sign. I bring that to the left-hand side and divide. So U of S is equal to minus kg. It's similar to what we did before. So I pulled a fast one on you. Okay, again, skipping some algebra. I have this thing here. As I mentioned last time, I multiply and divide by R. So I get a 1 over R. There's a minus sign missing, I'm sure. So that's why I get a 1 over R. And then I have a kgr here. That's important in this representation. It's a pole location. You know, when S equals minus this value, that's a pole. But people like to talk about time constants as well. So in control lingo, that's a time constant. So 1 over R is called the DC gain. As mentioned last time, after all, if you know this is a linear filter, and S equals 0 corresponds to DC. And it's not actually, there's a minus sign, so really minus. And so that's why it's called the, you know, I mean, it's called the gain. The word droop, I should know what it means, where the origins by now, sorry. Maybe somebody else can help me with that? Somebody else look it up. Not now, but we should all know the origin of that weird language. But anyway, it's a gain because it's a DC gain with a constant error, a constant, say, 1 degree error. If it was constant forever, then you'd get a constant change in valve position, you know, which would be 1 over R, minus 1 over R times that value. It's typically given in percentages. And typically, all generators contribute the same percentage of their nominal power output. You know? So you can read in the text. What they like to say is in per unit, which just means a percentage, you know. And so you'll see, like that. I forwarded you all this emergency warnings from was it NERC or it was NERC about 5%. Don't make it any bigger than 5%. You know. So in 2015. Okay, what would that mean? It would mean that a 1 degree change in frequency would be a 5% change in power output. You know. Now, I say, okay, so rho V I already said was the input. This is all DC analysis, so we made a notational assumption that in DC, valve position and power are the same. So, all right, so that sounds extreme because we said that the frequency is only going to change by 0.03%, you know, and so it's incredibly small changes in power, what we're talking about. But these are big mammoth guys. I mean, we're talking about, you know, many, many gigawatts of power. So you put it all together, it becomes real money, real power. Yeah, I mean, 5% times 0.03. Well, you work it out. I'll create a homework problem for you to think about it. All right. So, okay. So that's last time. Okay, so we could make a lot of simplifying assumptions when we were just interested in the steady state behavior to a disturbance. It was natural to set this equal to 0. We could ignore the dynamics between the valve position and the generator, but really we need to put everything together if we want to look at the dynamics of the grid. And so let's go and put everything together. So if we put everything together, and again, I need two things. I need the kind of thing we talked about last time, a disturbance response. If this thing gets jolted, how does it respond? And I also need to know this. What does the balancing authority expect when it sticks in an input, when it sends some signal here? You know, what will the behavior be? All right? And so first of all, I can augment this thing. It's actually, it's a simple change from here. Let's give it a name. When the book finally gets around to giving this a name, it has all sorts of different names. Let's call it rho of t. All right. So rho of t is the signal sent by the balancing authority, and I don't know what a capital rho is except for an r, and r has been taken, so we'll just call it rho of s. And I could do the algebra to prove this to you, but I know I'm going to get the same pole locations, and I also know I'm going to get a DC Kane of unity, because that's what integral control is for. You know, so I'm going to give you a review of integral control next lecture. But whenever you use integral control like this, you know the DC gain is going to be unity. It's just it's part of the setup. Okay, but you do the algebra. It's really easy to see here. I'm multiplying by r, and so that's why I get rid of the 1 over r. But you do the algebra again. You should be able to do the algebra. So that's the response for one generator. The frequency deviation and command from the balancing authority to its valve position. And first we have to multiply the whole monster times that other transfer function to get power. So I've done two things here. Again, multiplying this by this transfer function allows me to relates the power to valve positions. I've taken the 1 plus TS outside and said ST is TS. And then I have this. And what's going to happen is each generator is going to have its own features. And so I'm going to have to stick eyes everywhere. Because, see, we want the whole grid. We're not talking about one generator. Again, you all know this, right? It makes no sense to analyze this in isolation because that is a global signal. Now that's particular to a generator. T is particular to a particular generator. That's, it depends on a particular generator, and that does. But then you've got this one global, in the Droop game, a global signal common to all the generators in the entire eastern United States. That's what makes it so different than anything else. It's hard to believe. And the only reason that it ends up being there is because the rotational speed of the generator is locked in to the frequency of the grid. It's locked in. It's almost like mechanical coupling. It's amazing. It's hard to get intuition. I've got a video I'll play later showing how these things happen. But
they're assuming here this is a steady state case, right?
No, but this is not now. That's why I've got S's everywhere. So steady state means I set S equal to 0.
Although here we have rho v equal Pm, it's still not the steady state, or we just saw the condition.
No, where? Tell me. That's not steady state. No, it was only when I set S equal to 0. When I did computations to say, what if there was somehow an increase in load that was persistent, or a decrease in generation, what would all the variables converge to? That's what we did last time.
CH?
No, that's just, these are numbers.
TCH.
Yeah, that's just a time constant for the dynamics of the transfer function from valve angle to power, mechanical power. And so this models the transient response, the steady state, everything. So that's the beautiful linear systems. You change a dynamical system to algebraic equations, but this represents a differential equation. All right. S is differentiation, 1 over S is integration. Just like I went from here to here. That's all I'm doing. All right. So it's a bit of a mess then, isn't it? So let's give it a name, I guess. Let's just call it HI of S so we don't have to carry this horrible baggage around. And let's go through the same steps we went through in the static setting to try to put all this together. So So what did we go through? There was like 4 steps we required in the static analysis. So the first equation is unchanged. That there's a frequency sensitive load, which is just some constant d times delta omega, And so if this is negative, it says that there's some load that's shed, that these motors are spinning a little bit slower. And remember, each motor imperceptibly slower, but you've got hundreds of millions of them, and so they all add up. And then what was 2? So 2 is about the total power. Now here's something interesting. Okay, so so there's the sum of the deviations in the non-frequency sensitive load and the frequency sensitive load. It's a sum of all the electrical energy. Before I set out this conservation of energy, I can replace the E by the M. And you'll even see in my notes, I even made a mistake in transcribing this, but it's the electrical power that's conserved here, and there's that. And then we have to plug in this monster here, and that's sort of 3. What was 3 again? What was 3? So if you look in your notes, the third equation we needed was exactly relating the valve angle to power. But we've already got all of that here. I mean, we've done all that work there, so that's all done. So the last thing is we need to relate frequency and here's where things really change, because we have the swing equations. We can't just go and say, look at steady state anymore. We have to go and look at the dynamics. So we have the swing equations for each generator. Is this first order differential equation? And that looks scary because we have no idea what these are. The only way to handle this is to take a sum. Okay, and then we do it. So we just combine them all and we're done. So now algebra. All right. I'll put these down to slow me down. All right, so, but you all know what you're all way ahead of me, I can tell. All right, so I sum both sides here again, and that's again. Whenever I forget a delta, I'm sorry, because always we're looking at deviations. So here I would sum both sides, and again, the reason I sum both sides, it's a sum here that I understand, and the sum here will involve a sum of these horrible guys. It's going to be awful, I know. All right, so. Okay, first step of algebra is to sum both sides, and all I'm doing is I'm making a definition here that the sum of all of these constants that came from inertia, that came from rotational inertia, is I'm going to find that to be m. All right, that's the sum of all of them, and then from this, that's the sum of mechanical power minus total electrical power. All right, number one, and then we understand this from 2. And we understand this from, I'll put a star there. And you have to plug those monsters in. And you have to take Laplace transforms as well. I'm mixing time and Laplace transform notation. But let's do it. Okay, so this is in the time domain. I'm going to take Laplace transforms. Differentiation means multiplication by s. And I've got to go in and plug in that. And there's a minus sign, I guess, somewhere. which I left out. Mind if I put it in there? Okay, so I've just taken this first term out, and then the rho i's. Well, that's a mistake, isn't it? Because that's not rho v. That's the balancing authority signal, and we're going to assume that's common to everybody. All right. Now that might not always be true. There might be a gain in front that's different for each generator. But that can just, we'll ignore that. All right. So having that dependent on I, that'll mess things up. All right. It doesn't. Okay. All right. Yeah, we're going to get. That's the next week's. We'll explain that. All right. So I made a mistake there. If there'd been a v here, that would have been all right. Okay. And so then plus this. And rho of s. And then I've got a minus sign here. Right? 2, it's got the part here which is the non-frequency sensitive load. Again, that could be a jump up in load, or it could be a drop in generation, or it could be all sorts of things. It's a disturbance, really. That's a disturbance. I'll get back into that. And then plus, we all know that the frequency-dependent load, by definition, is modeled as d times delta omega. All right, did I miss anything?
Just that GPS.
Oh, where? You here?
That's focus.
Right there. I missed an S there, yeah. God. All right. Now this looks awful, doesn't it? But at least this is all designed, remember. Generators are mandated to set up certain droop gain parameters, and it's done in such a way that this is not so bad, You know what I mean? That all the pole locations are not that far apart, things like that. So this thing turns out to not be bad by design. All right, so I can kill this shit, can't I? Excuse my language. Happy with the algebra? Okay. No. All right, tell me what you don't like.
You just don't like algebra.
I don't like algebra either. I don't know why I feel like I have to do this, but I do. I feel like I have to do it. If I don't do it, what would I do? What would I say? Because you have to see where this came from once, All right. Okay, so we need to simplify something. And so we're going to need to. What conventions did I make? This can even go, can't it? All right. So each of these HIs was actually a second-order linear system. Let's approximate, pretend the valves don't matter very much, and pretend it's a first-order linear system. And by design, their pole locations are all similar, which is true. And so we could actually approximate the entire sum by a first-order linear system. If these guys had all the same poles, if these were all just 1 over s plus 1, then you would have an n over s plus 1. And if all the I'm sorry, the sum of the RIs, you'd have a sum of if these were all the same, you would just be summing the 1 over RIs, and you just get one little simple first or second order filter. So let's just make that approximation. So let's just write so this horrible sum here will be some Um, I'm going to put another symbol there. Okay, so this complicated-looking transfer function, I'm just saying pretend it's first order, which means I've ignored valve dynamics, and I've assumed all of the droop dynamics are the same. They all have the same poles, which is an approximation, but not too far off. And here again, all of these have exactly the same pole locations, and we're approximating by first order, assuming the valve dynamics are fast, right, compared to the droop dynamics. And that's reasonable as well. Now, we know what the DC gain of this transfer function is, so we know B. We know B is equal to, I mean, this was the DC, this was the transfer function from power deviations to mechanical power. So if you go back and look at your notes, we know B is D plus the summation I equals 1 to N of 1 over Ri inverse. We derived that. And if all these HIs were the same, then this constant M would be N. So M is probably N. There might be scalings, you know. There might be scalings. It might not be N, but you know, something like that. With this model, you could guess that. You know, I mean, it makes sense that the balancing authority would scale down the reg signal for small generators according to big generators. So this would only be for homogeneous population. Okay, and so what have I missed? I lost some terms, right? So I got this, approximated it. I got this, approximated it. That I left out, and that I left out. And I need colored chalk, I think. So, minus these two terms. Okay, and then we can go through and solve this, right? Yeah.
So I mean, I'm not getting like how do you, so HI, on what basis is HI the same? Because
we designed them, okay? So we set droop gains and so remember these came from two components. Yeah. So there were valve dynamics, which we'll assume are fast.
Yeah, okay.
So if they're not fast, you have a crappy generator, you should upgrade.
Yes,
and the rest of it's the governor dynamics, which are designed very carefully by all sorts of rules. There's an integral gain, which is going to be set by standards, you know.
So when we derived the governor dynamics, we got the equation 1 over 1 plus STI, right?
No, I mean, so the main, oh boy, I hate to write this down again, but the main thing that we saw was this. So there was a droop gain, and there was a gain in the integral control system, and you're going to have standards to make sure these are all pretty much the same.
This is my HI.
That's part of it. This was the governor response. I don't want to rederive it. It's in your notes. The governor was this. you know.
Which means
And the thing is that this is all going to be set by standards to make it simple.
so the only thing this means that we change like Ri is like the root gain, right? 1 over Ri.
Yeah.
So we have kg of I
So
equal
K-
to 1 over
So
Ri.
so you can make sure these are all the same for all the generators. So if you put i's in there,
Yes,
the approximation is say t is the same for every generator, which isn't a bad approximation. Okay, they're all similar. These time constants in the order of 10 seconds or something, or a few seconds. Yeah. All right. All right. Yeah. But I mean, assuming everyone plays by the rules, and okay. So I'll kill that. So here it doesn't matter that I know what B is or M. It's just I need some approximate dynamics, and maybe it's not exactly a first order system, but you will see it's a very reasonable approximation. We can see by actual observations of the grid, we will see, maybe not, maybe next lecture, that it's reasonable. So I'll kill this. Okay, so when you unpack all this, you're going to get some, and this is star star. With some of these two terms. So you'd have to rationalize this. Shall we rationalize? We're going to have to multiply everything through by this to make it, and then go through and solve it. And I guess we should do it. So we're going to get, first of all, we're going to get a 1 plus STG times S times M. And I'll get a minus B and then I get this. Okay, all in algebra, you don't have to be secretaries. You can just sit back and look, because I've carefully written this down in the notes, so you don't have to do this. All right, so then you go through and you look at this and stare a bit, and I've got something in front of that. I don't care about that. I can put all the terms involving delta on the other side and divide. And where are they? I've got that depends on delta. And that depends on delta, and we see we're getting a second order response. Let's collect them all over. So I'll get a plus B, I'll get a minus blah, anything else? Delta W, that's it. All right, and we can just now quit. And I won't do any more algebra, because you can do it yourself. I've got a transfer function on rho of S. Yeah, I dropped a term. That's saving chalk. All right. So that's a second order polynomial. You can all agree with that, because I get an S times S there. And all I have to do is say that. So I've got an M over A of S in standard signals and systems notation, times rho of S, and minus 1 plus S Tg over A of S times delta P load non-frequent times the disturbance. Again, I wrote load, but this could be because of the clouds. There's some shock to generation as well as load. Anything that's a shock to load, both from generation or from supply, is going to be here. So that's a disturbance. That's the grid level control. That's what the balancing authority sends in. Oh my God, time is up. The line has started. But all right, yeah, it's just now, huh? So if you're a control person, hey, a 0 in the left half plane, overshoot. And you're going to get, depending on how big TG is, we'll talk about this next time, you get big overshoots, undershoots in frequency given a disturbance. And here you say, oh my God, it's a relative degree 2 system, blah, 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 blah. It means certain control strategies are needed. So next lecture, we'll talk about the implications of this structure. But somebody help me erase the blackboard, because we have to let him in. All right. So we'll get